Okay, welcome. Let's get started today. I'm Maya Gupta from Electrical Engineering, and we're delighted today to have Erik Sudderth, who is a faculty candidate in both electrical engineering and computer science today. Erik started out with doing his BS in electrical engineering at the University of California, San Diego, and then moved on to MIT, where he worked with Al Wolski and Bill Freeman. Took his PhD in 2006, and has since then been postdocing at Berkeley with Michael Jordan and Stuart Russell. Among his many honors, he was an NDSCG fellow and a Barry Goldwater scholar. So okay, let's get started.
Okay, thanks, Maya. So today I'm going to be mostly talking about a problem called visual scene analysis. So here we have two images in which a person has gone through and segmented out objects that are interesting to us in the world. On the left we have some trees in front of a building with the sky above. On the right we have a field with some people standing on it and some kites up in the sky. And so the goal of this work is to sort of try to build automated systems which can do this kind of analysis in an automated way. And this has applications in all sorts of things, from web search and image retrieval to surveillance to robotics. And also there's a sort of lot of interesting connections to related problems that show up in machine learning, AI, signal processing, that sort of the issues you explore in this application are relevant in those domains as well. And this is actually one of the oldest problems that people thought about tackling in computer vision, going back to some really ambitious work from the 1970s. And so these here are some figures from a paper by Tannenbaum and Barrow in 1977. So it's a little hard to see this old reproduction of the image, but this is a hallway in which there's a wall with some pictures on it. Next to it, there's a door. And so what they do is they begin by sort of defining a set of constraints about how objects relate to each other in a pairwise way. They label the bottom of the image as a baseboard. Then there's a sort of constraint propagation that goes on. And in the end, they end up with actually a pretty good labeling of the image. So they say, no, this is a door, here's a knob next to it, some pictures on the wall. It's not perfect. They also think there's a bunch of little tiny pictures hanging on the wall next to the big ones. But nevertheless, this is sort of an exciting result. So unfortunately, these sort of systems, except for sort of some very toy examples like this, never really took off. And I think there are really two problems here. One is that computers in the 1970s weren't what they are today. But the second is that people didn't know how the sort of statistical models and techniques to be able to learn these models from real images. And so instead of this, they ended up having to define everything by hand. And so here's some examples of the sort of rules that were underlying that system I just showed you. And they have things about what regions can potentially be above each other, adjacent to each other. They also have notions of what regions can be next to each other depending on whether or not there's contrast, where contrast is sort of defined by a sort of single manually set threshold. And so with these sort of rules, you can get sort of results on a single image or a few simple images, but the system ends up just being too fragile. You can't write down a set of rules like this that sort of robustly capture a wide range of real-world scenes. And then so for a while, computer vision went in some different directions. And so there was a lot of work in the 80s and early 90s on 3D geometric reasoning. And so the idea here is I have a sort of detailed model, something like a CAD model, of the object I care about. And now given an image, I want to match the 3D pose to what's depicted in the scene. So here there was a 3D model of a razor that was matched to several instances in this image. On the right, we have some more complicated objects like bottles. And so there's some really nice work, foundational work that went on here in sort of understanding perspective geometry, efficient matching algorithms. But in a sense, it's a sort of much less ambitious problem than the scene interpretation one. We're going to assume we have particular object instances. And so the system might know about this particular bottle made by this manufacturer. If you give it a slightly different size and shape of bottle, it's not going to be able to recognize it. And there was another shift of focus in the mid to late 90s back to object categories. And so this really came with the introduction of probabilistic methods to computer vision. And so two sort of categories that have each received lots and lots of work in this domain. One is handwritten digits, in which there's this large MNIST data set, has 60,000 training examples. Also frontal faces, and so one of the sort of classical papers in this regime was a system by Viola and Jones. And so this has really become a major application domain for statistical machine learning. You pick your favorite machine learning method, there's probably been lots and lots of papers applying it to this sort of object recognition. And so the models that are learned by these systems are essentially template models. And so the idea is I have a little rectangle that says, has a classifier which says, is there or is there not an object, say a car, in this rectangle? And I scan this rectangle across the image at all sort of locations and scales until I come up with an instance of the object. So say you detect the rear of this car right here. And then, in fact, you'll get a whole bunch of other detections. Typically, you'll have a bunch of partially overlapping detections. There'll be a bunch of detections here. Often, there'll be false alarms. So here, a car might have been hallucinated up in the clouds in the sky. And then some sort of post-processing has to go on to sort of deal with these overlapping detections, figure out exactly how many objects are in the scene. And so there's been some very promising results with these techniques, but also there's some real limitations. One is sort of a computational scaling problem. If I have to build one of these sliding window classifiers and slide it across the image for each of thousands of object categories, that takes a long time. Another is that to get sort of classifiers of this form to work well, you typically need a lot of labeled training examples. And so in the case of handwritten digits, the US government really cared about being able to read your zip codes automatically. And so they were willing to put the resources behind collecting a big data set. But there's a lot of other object categories that are both much richer in terms of their internal variation than digits, and also that there's just not going to be that many labeled examples. And also this sort of idea of this sort of rectangular sliding window classifier, it works good for some objects, not so good for others. So for example, if I want to detect buildings, what's the sort of canonical rectangle that a building fits in? They come in all sorts of shapes and size. There's spatial structure there, but it's more complicated than just a sort of fixed template. Or on the other hand, there's objects like if I want to do sort of interpretation of this scene, often knowing that this is the road in the foreground is really important. But if I look at a local patch of this, it's just gray. It doesn't really tell me anything. So the way in which you recognize the road is sort of from it being at the bottom of the image and its relationship with the other objects, that there are cars sitting on top of it. And so the work I'm going to talk about tries to take a different approach to scene analysis, in which we have an integrated model of a scene as being composed of a collection of multiple objects. These objects are, the internal structure of these objects is in turn described by a set of parts. And then these parts are finally related to features. And features are going to be the things I can measure from the image in a low-level fashion. And so I think there's a number of advantages to thinking about scene modeling in this integrated way, and I'll get to some of these as the talk goes on. So I'm going to begin by taking a little detour into probabilistic models, and in particular a class of non-parametric models that have some really nice properties in these application domain. And then I'm going to move on to a set of projects that sort of build increasingly rich models for the structure of visual scenes. And so a lot of the models I'm going to talk about can be phrased in terms of what are called graphical models. And so what a graphical model is that we have a set of nodes, and these are going to correspond to random variables, the things I care about in the problem, and the edges are the dependencies among them. And so as sort of the simplest sort of very high-level model for image data, you can think of a graphical model where at the bottom I have a bunch of data corresponding, in this case, to say that in different training images. So I have some features for each one. Underlying these things, I'm going to assume there's a set of object appearance parameters. And I don't know what these are. This is what I want to infer from the data I have available to me. And typically also, people put in some sort of prior knowledge or regularization to this process. This is specified in terms of what are sometimes called hyperparameters. So if you combine this prior knowledge with the likelihood model relating your object parameters to the image data, you can combine those with Bayes' rule to get a posterior distribution over, given my data, what are likely and unlikely future versions of this model. And so just a sort of notational shorthand, often so people, rather than drawing out these individual nodes individually, they use this plate, a box here, to denote this replication. So in principle, you can sort of think about building a really wide, rich range of models with this generative structure. In practice, though, a lot of sort of what's been done has ended up being sort of fairly simple. And so to pick a sort of classic example, we can look at eigenfaces, which is some work from the early to mid-90s. And so the idea here is I'm going to try to model the appearance of cropped images of frontal faces. And I'm going to represent these as the sum of a mean face. So this is this sort of androgynous face right here, as well as a sort of a linear combination of a set of basis vectors. So these are going to try to model the different way in which facial appearance varies. And because you learn these basis vectors from an eigendecomposition, they were sometimes called eigenfaces. And so again, mathematically, we just have the observed face image, xi, is the sum of a mean plus a linear combination of these eigenfaces. And typically in the learning process, people said that, well, they assume that these weights in this linear combination are just assigned a Gaussian distribution. And this is not because if I take sort of Gaussian random combinations of these faces, I get anything that, of these basis vectors, I get anything that looks like a real face. You get things that look kind of like faces. You also get a lot of stuff that looks nothing like a face. This is really just sort of a thing that makes things analytically convenient. And so this model captures some things, but it's really overly simplified. This sort of linear combination in the pixel domain that doesn't capture the interesting things about what make faces. And so these sort of very simple modeling assumptions are going to limit the expressiveness of what our systems can ultimately do. And so in particular, there was no follow-on paper about eigenbicycles. There's a really good reason for this. So even if I sort of factor out the sort of 3D viewpoint variations, it's just there's a lot more, faces kind of all look almost the same. There's two eyes and a nose and a mouth, and they're all always roughly the same size and shape. There's so much more internal variation of bicycles in terms of what the wheels are like. There's baskets, other sorts of accessories. So there's a lot of structure here. But if I just sort of take pictures of bicycles and start taking linear combinations in the pixel domain, I'm not going to get other bicycles, I'm going to get junk. And so we really need to think about other ways of sort of building richer models for object categories. And to do this, I'm going to borrow some tools from the non-parametric statistical literature. And so the model here, the bottom layer of image data and the top layer of prior knowledge haven't changed. But in the middle, I now have something that's a little richer. So I have, for each, rather than having a single set of parameters, I'm going to say that there's going to be a set of parameters for each of my observed training images. And the intuition here is that these are going to capture the way that not all bicycles look the same. There's sort of internal differences in their structure. And then to couple these together, there's going to be an unknown probability distribution. And so this is going to be a probability distribution over what the parameters for some new image that I see are going to look like. This is essentially a random function. It's an infinite dimensional object. So potentially things are much more expressive here. And so at a cartoon level, you can think that even if your prior knowledge is very simple about what the object's going to look like, this distribution over appearance parameters might end up taking a much more complicated form. And so it can grow in complexity as I get more and more data available to me. And so in the context of visual scenes, these random distributions are going to turn out to essentially be combinatorial objects. So if I think about decomposing an object into a set of parts, there's this uncertainty into sort of how many parts should I use and what are the sort of relative locations and identities of those parts. Similarly, if I think about wanting to parse a scene, there's uncertainty as to how many objects are in the scene and where are they located relative to the camera. And so we're going to model this by placing discrete distributions on random sets. So rather than having sort of a simple finite parameter vector, we're going to have something much more complicated and rich that lets us get more out of data sets. And the particular form of this parameter vector is something that I'm going to use in a lot of this work is something called the Dirichlet process. So again, this is a distribution over parameters. It's a discrete distribution, so these are Dirac delta functions centered at particular parameter values. And each one is going to have some weight. So these pi k's are positive numbers. They sum to 1 because it's a probability distribution. And the prior distribution of the Dirichlet process says that these pi k's are sampled from what's called a stick breaking process. So that is I have a unit length stick of probability mass. The first weight is going to be some random proportion of that stick. I'm going to sample a number between 0 and 1 and break off some random proportion. Now I'm going to take the part of the stick that's left, and I'm again going to break off another random proportion of it. And then I'm going to continue this process recursively. And I'm going to keep, because there's less and less of the stick left, these sort of numbers are going to get smaller and smaller on average as I go down the chain. And if I pick any particular significance level, say how many of these parameters contribute 99% of the mass of my distribution, there's going to be some random finite number of them that do that. So when you first see the stick breaking construction, it seems kind of mysterious. Why is this a good idea? And there's sort of several things that come together in the Dirichlet process. And so the first thing is when you think about non-parametric models, a non-parametric model is not a model that has no parameters. So in this case, it's a model with infinitely many parameters. Another way of thinking about it is I want my model to get more complex as I get more data. So given a small amount of training data, I'm going to get fairly simple, robust predictions. And in the Dirichlet process, this is going to be by only using a few of the samples of the stick breaking process, the ones with the highest probability. But then as I get more and more data, I'm going to be willing to use more and more of these sticks. And this is going to give me a richer, more expressive model. And so this particular way of doing this construction sort of balances the goals of being flexible but also tractable. And so there's actually a fairly extensive statistical literature showing that there's a lot of nice asymptotic properties of this Dirichlet process prior. And it also leads to sort of simple, effective computational methods. So the nice thing is, I'm not going to have to do some sort of combinatorial model search. I'm going to be able to sort of search over possible discrete structures in an integrated way. And this lets me scale to sort of larger, more interesting data sets. OK, so now I'm going to move into talking about how I can apply these ideas to different sorts of visual data. And so I'm going to begin by setting aside scenes and thinking about images of isolated objects, and talk about how, by sort of, if there are multiple object categories I want to learn about, how I can share information between them to improve the quality of my model. And then I'm going to come back to scenes with multiple objects and the scene parsing problem. And finally, I'm going to conclude with a few sort of future directions that are suggested by these ideas. So again, the problem we're interested in is visual object categorization. We don't want to recognize a particular object instance. We want to learn what it is that separates bicycles from llamas, from cannons, from all the other objects that we see and recognize and interact with in our daily lives. And we want to learn appearance models from these objects from a potentially small set of labeled training examples. And so we're going to describe the internal structure of objects with parts. This is, again, a really old idea in both the computational and human vision literatures. So going back to sort of simple mass and spring models from the 1970s, to later work on what are called generalized cylinders, so modeling the structure in terms of sort of elliptical structures, onto sort of more recent probabilistic approaches. But one problem that shows up in all of these part-based models is this question, well, how many parts should I use? And remember, it's not a trivial problem, because I don't want to learn how to describe just this particular elephant or this particular bicycle. I want to generalize from a small number of examples. So I want to learn to predict what are the sort of features that are going to be shared across all elephant categories, and what are the things that are particular to this particular elephant. And so in order to learn models, these sort of part-based models, we're going to begin by sort of extracting a set of features from the image. And this is good. The idea here is just to give us a little invariance to lighting, pose, things we think are not related to object category. And so there's essentially three kinds of features. And so there's essentially things that are on the corners of objects, sort of homogeneous regions, as well as edges. And so in all of these cases, these ellipses here that you see are the sort of size and shape of the ellipse is determined in a low-level fashion. You're essentially adapting to what you think is going on in that particular part of the image. Okay? And so with each feature, there'll be some 2D location. So where did I detect this feature in this particular image? Then we also want a way of describing the appearance of these features. And here we're going to adapt a method from the computer vision literature called the SIFT descriptor. The idea behind SIFT is pretty simple. So what I'm going to do is I'm going to compute gradients of sort of what orientations there are at different parts of the image plane. And then I'm going to compute histograms of them. I'm going to do this in a particular way that gives me some robustness. And the idea here is, again, to get some robustness to the fact that I may not have done a perfect job of lining up my feature right on that corner and get a little more slop, something that's a little more descriptive. And so then through a vector quantization process, these features are mapped to what are sometimes called visual words. And so this is a discrete thing describing the appearance of a particular feature. And to get some intuition for this, on this images down here, each color corresponds to a different visual word. So you can see the purple ones typically show up in the upper left corners of the monitors, the green in the lower right, and so on. So this is the kind of signal we're going to have available to us to sort of learn about object appearance. You can see that there is some noise in this low-level feature extraction process, and so our later models are going to have to be robust to that. So I'm going to begin by describing a sort of very simple generative model for objects, and then elaborate on that. So we think of an object as a set of parts. So in this case, there might be a simple 3-part model for a bicycle category. For each image, we're going to then choose a reference position. And this is just modeling the fact that the object might be in a different location depending on where I pointed the camera when I took the photo. Then for each feature, there's going to be a 2-stage process. I'm going to pick one of that object's parts, and then I'm going to sample from a location and appearance. I repeat this process, and I keep generating sets of features. Okay? And so there's going to be each part is not going to have just one feature, a whole set of features. The number will vary from image to image. And what the parts are going to do is capture the fact that in certain locations, features have certain particular appearances. So mathematically, you can express this model I've just described in terms of this Dirichlet process prior. And so this random distribution now is going to be describing the set of parts. And so each part is going to have some particular position and appearance model. And then I'm going to have a potentially infinite set of parts. I'm going to learn from data how many I should actually use to get a good generalizable description. Then the rest of the generative model, for each image, I'm going to sample a reference position. For each feature, each of the features, I'm going to choose a particular part. And then, given that part, I'm going to sample its appearance and position. And so if you haven't seen this graphical model structure before, the details here aren't very important. What is important is the fact that it has a sort of modular form. So I sort of took the part of, oh, there's parts, there's locations of the objects, there's appearance, and I sort of put them together. And so as I build sort of additional pieces into the model, this is going to let me do so in a way that lets me reuse work I've done before. And so finally, there's always a question of sort of, well, what do I have to give the model? How much prior knowledge do I have to do in terms of tuning parameters? And the good news with these models is not very much. Essentially, there's sort of two sets of hyperparameters I have to set. And one is saying something about essentially the scale of the image. So what's the size of the image? And the other thing is sort of a sort of bias towards what scale I expect the parts to be. Do I expect the parts to cover most of the object, to be very small, somewhere in between? Okay? And then other than this, all the details of the model is learned directly from data. So here's an example I took a sort of simple data set where there's a bunch of frontal faces that are aligned and decomposed them into a set of parts. And so here, the ellipses here are the covariance ellipses of Gaussian distributions. This is showing the size and shape at which features for a particular part are located. And here I've shown with 4 training images, 16 images, and 64 training images. And so what you can see if I have a small number of training images, I get a fairly coarse-grained description of what the face looks like, a small set of parts. And then as I get more and more data, I get finer and finer descriptions of the internal appearance. These are sort of coloring the features according to which part they came from. It's probably a little hard to see on the projector, unfortunately. And so what you can see is that, again, you get this sort of non-parametric property of these models, that as the number of training images grow, the number of parts that I'm using to describe the model, and thus the richness of my appearance model is also increasing. OK, but I'm not interested in just single object categories. I want to categorize lots of objects. Yeah?
You sort of expect the features would align with the intuitions of the important parts of the face.
Yeah.
They don't look like it in this image.
Oh, the features down here?
Yeah.
Yeah, so in this case, actually, so I've come to dislike this sort of sparse feature extraction process. And in some of the work I'm doing now, I've gone to different low-level feature representations. And so they're extracting things that they actually work pretty well in terms of recognizing objects, but they don't correspond to sort of something that's semantically intuitive. And I think there's sort of better things to be done in the same framework with the low-level feature engineering. So if I turn to think about sort of recognizing multiple object categories, so the question comes up, so suppose I have a whole bunch of images of llama faces. And so I've used these to train a world-class llama face detector. Okay? And now I give you this new image of this class you've never seen before. Do I have to start from scratch, or is it somehow easier to detect other examples of cows, given that I know a lot about what the internal appearance variations were within the llama face category? And so there's lots of ways you can think about attacking this problem of transferring knowledge between categories. And a particular one we've explored is the idea of sharing parts. And so if you look at object categories, even if they're globally different, there are often local regions of the object that are similar in appearance. And so noses and wheels are a bit cliched examples, but if you look at the features that are detected on real objects, there are actually a lot of examples where this occurs. And so the question is, by sort of leveraging this sort of local appearance similarity, can we do a better job of learning models of object appearance? And again, we're going to use Dirichlet processes to allow us to learn from data how many total parts there should be, as well as how many of these parts should be used by each object category. OK. So in sort of pictures, the way that this hierarchical Dirichlet process object model looks is I have a set of global parts. And then I'm going to compose each object category by taking a subset of these parts. So in this toy example, there might be a wheel part that's shared between the bicycle and cannon categories, as well as some other parts that are independent. And then given these parts, the rest of the generative process is the same. For each image, I sample a location of the object. Then given that location, I sample a bunch of features. Okay? So to sort of explore this model, we looked at a set of 16 object categories where you could hope to have sort of the sharing to provide some benefits. And so they're coarsely divided into 3 high-level groups. There's 7 sets of animal faces, 5 animal profiles, and 4 vehicles, or things with wheels. And so each training image is labeled with the object category it comes from. But we don't tell the hierarchical model about this coarse level structure. As far as it knows, it's just a list of 16 object categories. And so one of the questions is, will it uncover the fact that some of these are more similar than others and use that to get better models? And so we can look at a few. If I take 30 training images for each of these categories, I think it learned something on the order of 150 shared parts. And here's just a couple of them. So here's an example of a part that this is the position distribution of where features from this part show up. And then there's also the appearance distribution is a little complicated to visualize directly. So what I've done is I've taken all the features from all these images and plotted only the ones that are most likely to have come from this part. So in particular, this part is essentially modeling features that show up around the wheels of these vehicle categories. There's another part that, for the most part, is modeling features that show up around the mouth and lip regions of the object categories. And so each object category is defined by reusing a common set of parts. And so this lets me compute a pairwise distance between object categories. And so to visualize this, one way of doing it is to use multidimensional scaling. And so here, if the Euclidean distance between 2 points is really, if they're nearby, that means there's a lot of overlap in terms of the parts they share. If they're far away, that means there's not much overlap. They use different sets of parts. And so here you get a fairly intuitive clustering structure. The faces are all here on the left. Within the faces, there's a subset of the cat faces, as well as the sort of animals with more elongated faces. We have several of the animal profiles over on the right, and some of the vehicles up in this corner here. Another way of visualizing these same distances is with a hierarchical clustering or dendrogram. And again, there are sort of 4 fairly intuitive clusters here. So we have the elongated faces, as well as 4 other types of faces, vehicles, and profiles. There's 2 categories, the wheelchair and llama body category, that in this case didn't end up sharing many parts with any of the other categories. And so to get a sort of more quantitative measure of whether the model is doing something interesting, we looked at a detection task. And now, so the challenge is, given a test image, you want to say, is it the object category, or is it some other thing? And so we have a whole data set of kind of background patches from natural scenes. Okay, so you want to distinguish between these 2 at test image. And so we can quantify the performance here by an ROC curve. So being in the upper left is the best performance. And so the first thing to notice is that the blue model is the model I just described, in which parts are shared among object categories. The green model is a simpler model in which I build an independent durationally processed part-based model for each category. So learn from each independently, no sharing of parts. And so here with 6 training images per category, you get a fairly substantial boost in detection performance by this sharing. In fact, interestingly, so the solid curves are this full model that models the position of features. The dashed curves are sort of a simpler baseline model, what people sometimes call a bag of words model. So I model the appearance of features and don't ignore the fact that they have particular spatial locations. And so if I share parts, I get a fairly substantial gain in performance by having this sharing, actually by modeling position. But actually, if I don't share parts, I do worse by modeling position. So in this case, there's some overfitting going on with the small training data. And here I'm plotting area under ROC curves, which is a standard summary statistic, versus the number of training images. And so here you can see with 4 or 6 training images per category, there's a very substantial boost from sharing. But even with as many as 30 images per category, there's still a very noticeable gain. Okay. And I should also point out that sort of refinements of this bag of features approach, which corresponds to this green curve here, give quite good performance on many of the standard test data sets. So this is sort of not trivial to be able to do better than this by, yeah.
Question. Remind me how you're actually taking the relative positions of the parts into account. You're picking a position for the parts, right? But how do they depend on each other?
So it's essentially there's a hidden latent variable, which is the location of the object in that particular image, and that's sampled as part of the learning process. So you're simultaneously inferring where the object is located and what they are. And so in this data set, we didn't need to do that because the images were all centered. And so in the scene models I'll talk about next, you'll see there's multiple objects in there, and there this location variable becomes really important.
So you just take into account where the object is, not that, one part of the object is above another and things like that.
So it's what people sometimes call a star topology. So essentially the parts are all rigid within the object, and then as I move the object around, they move in a rigid, coherent way. So that is capturing the fact that one part is always above the other, because as I move the object, both parts shift in a rigid way. And there's some additional, because the parts are sort of have this Gaussian distribution over where features exactly show up, that gives us robustness to sort of local deformations in the object. It wouldn't work well for sort of wildly, sort of very articulated objects.
What if you flip an object from left to right? Then it wouldn't work.
So in this case, so I'll get later in the talk, I'll talk about more complex transformation distribution. Actually, for most of these object categories, it works fine if you flip from left to right because there's a lot of symmetries. But there's other sorts of in-between 3D rotations that don't work, and I'll get to that later on. And so actually, this is a good time for other questions if there are them. One other point I wanted to point out is that this sharing, in addition to sort of giving me computational gains, has some real advantages in terms of how complex the models I end up with are. So here I'm showing as a function of the number of training images per category, the total number of parts used. So the green curve is if I don't do any sharing. The blue curve is if I share parts among categories. And so at test time, everything I do computationally grows linearly with the number of parts. And so the hope is that as I start scaling up to lots and lots of object categories, I'm not going to have to I want to have 1,000 categories, I'm not going to have 1,000 times as much computation. I'll be able to sort of get some sort of more manageable scaling. All right. I'd be happy to take any other questions before I move on. Yeah?
You said the complexity of model grows with the trained data size.
Yes.
So do you have any regularization means to fight too large complexity?
So that's exactly what the stick breaking prior and the Dirichlet process does. Is it gives you a prior on sort of there's always a trade-off between how well my model fits my data and how many components of the model I'm doing. By using more components, I can always increase the sort of likelihood score at which I fit the model. And so the Dirichlet process trades off these two things in a way that is computationally easy to deal with and also has some really nice theoretical properties. So there's a lot of papers in which you can show other ways of sort of trying to do this trade-off can get you into trouble. And the Dirichlet process works well. Yeah. Yeah.
I guess this was a similar question to the one that was just asked about. And I guess what you're essentially saying is that for a given class of deformations, if that was then accounted for in the actual model, you'd be able to account for that.
Exactly.
So,
yeah.
But then the question really is as a function of the amount of training data, how well can you learn? And as you have more training data, that is affected by these kinds of deformations.
Yeah. And so that's a good.
You have an affine deformation and then 3D rotations.
Yeah, and that's exactly one of the directions you'd want to go. And some things I'm working on now, I've been thinking about how I can do more complex classes of deformations and still deal with them in a tractable way. And so this was really just stuck sort of with sort of simple scale normalized data sets for an initial proof of concept. But yeah, that's something that easy to extend in principle. In practice, there's a lot of details you have to get right.
The question then is, if that's correct, then the question is, in the absence of a true 3D model of objects, where do you expect the sort of sample complexity to go when it's the case that training data can be affected by all of these arbitrary deformations?
Well, it depends a lot. There's a lot of issues there. So one is how complicated the structure of the object is and how much within class variability there is. Some objects are intrinsically easier to learn about than others are. And also, there's this question of sort of what data do I use for learning about multiple views of the object. And so one thing that you can imagine doing is just getting a whole bunch of random pictures of cars. I have car A and car B and car 3 that are viewed from totally different viewpoints. And then you have this essentially difficult correspondence problem of figuring out what the 3D mapping is between them. But, you know, maybe that's a harder problem than we need to solve. We can really think about using stereo or video data, exploiting these sorts of things where you get the correspondence between multiple views in a sort of trivial way. And I think that's a sort of potentially exciting way to think about getting the data that lets you generalize across views in a way that is sort of more manageable.
Yeah, I mean, it seems to me that this is a meta issue of similar to choosing a kernel, right? At some point, you have to make some choice based on the training data that you have.
Yeah, you are going to have to make some choice, and so this is where, you know, I don't. You don't want to try to relearn from data what an affine transformation is. We should take all our knowledge about perspective geometry and how these things relate and exploit that. We want to learn from data the things that are hard to describe, which is, you know, what's a chair, not how does a chair change as we look at different viewpoints. But you know, this is the kind of problems people are just beginning to think about, and there's a lot of work to be done. Okay, so now I'm going to sort of move away from these isolated objects and think about multiple object scenes. And so, again, we're going to try to build an integrated model, which a scene is a collection of objects described by their internal parts, which are finally related to low-level features. And for me, there's sort of a number of reasons why I'm interested in doing this, but one of the biggest is because if we start to think about the sort of training data that we have available to us for visual problems, and it's probably going to be available for the foreseeable future. And that there's a sort of relatively small set of images in which people have gone through and labeled them in detail. So in this case, they might have, the purple corresponds to building, the green to trees, the red to cars, the blue to roads. And then maybe you have some more images in which there's some sort of partial labeling. So maybe they went through and found just the cars, or here they picked out the road but didn't tell you what was going on in the upper part of the image. And then I have an essentially limitless supply of unlabeled images. More than we can sort of deal with computationally at this point. If I think of objects by themselves, then this unlabeled data and all these white parts of this partially labeled data are useless to me. I have to throw them away. But if I sort of think about modeling scenes together, we can hope by sort of learning about relationships among object categories to sort of leverage this sort of more heterogeneous data and learn better models. And so now when I think about building a model for multiple object scenes, there's two immediate tough questions that show up. One is we don't know how many cars there are. In a sense, that's the thing we care about most is estimating how many cars are in the scene I see. And we also don't know where the objects are located. So depending on where the camera, there might be cars at the top of the image, or the middle, or at the bottom. And so to attack this problem, what we're going to do is we're going to define a global Dirichlet process that's going to model objects in a canonical or object-centered coordinate frame. So this says, this is what the object looks like if it was right in front of my camera when I took the picture. And then we're going to generate images via a random set of transformations. So we're going to take the pose parameters of the object and we're going to shift them according to the sort of transformations. And so this comes back to your question, Jeff. So in the work I'm doing now, we're just doing a simple shift of the mean, a simple translation. But in general, I absolutely am thinking about doing sort of more general classes of affine transformations in this framework. And so the model that we ended up calling the transformed Dirichlet process, there's now a sort of global model that has three things. There's a set of object categories, which here I've encoded according to the colors. So there's a red, a green, and a blue object. Each one is going to have a set of parts. So the red object here might have 4 parts. The green has 2. The blue has just 1. These are these solid ellipses. And also, we're going to have a model of the typical pose of objects. And that's what these dashed are. So in this case, the red object might typically show up in the bottom part of the scene, the green more in the upper region, and the blue in this upper left corner. Then for each image, I'm going to take a random number of copies of each object and put them down in random locations. So in this case, there might be 2 copies of the red object, here just 1. Here I have 2 copies of the blue, none at all. Okay? And now, given that I've fixed these object locations, now I'm going to generate the features that I observe in the image. Okay? And then, of course, the data I have available to me is these features, but with the object category labels removed. I have sort of these appearance labels that are loosely correlated with object category. And now I want to try to invert the process, going back up to what set of objects generated the data I have available to me. So if I run a learning algorithm on this model to a set of street scenes, here's examples of the sort of models I get. And so each of the object categories I define might get broken up into multiple visual categories. So here, this thing here is modeling the fact that in a lot of these images there's a building that's covering the whole top of the frame. And that's what the spatial coherence is. Here, similarly, we have a model for what the road looks like. There's sort of less structured models for what trees look like. There's a very detailed model for the internal structure of cars, so how you have features, different features at the wheels and the windows and the front and the back and so on. And so to actually learn these models, we've developed an example of what's called a Rao-Blackwell-Gibbs sampler. And so what the sampling algorithm is doing is it's dynamically creating and deleting objects and parts, and it's doing this using a set of assignment variables. And so you can think of these as pointer variables. For each image feature, I have a pointer which says which object instance it comes from, as well as which part of that object. Similarly, for each object instance, I have a pointer which says which global object category does it correspond to, as well as where is it located in this particular image. Okay? And so by sampling these sort of small set of variables, and when I sample an assignment, I consider the possibility of creating a new object instance or creating a new part. The probabilities for this come from the Dirichlet process and give me a nice way of searching over scenes at various moments of the project. And so here's examples of interpretations where in the street scene, here it put down several copies of the car cluster to model the several cars. Here it put down just one to model the car parked right there. And so the nice thing about what this Rao-Blackwellization process is there's lots of other variables in the model that are sort of continuous and high dimensional. I don't have to sample them directly. I can integrate them away analytically. And this makes the sampler work much faster and more robustly in practice. Do you integrate out? So for each part, there's a Gaussian distribution over the position of features and a sort of high-dimensional multinomial over the visual word vocabulary. And those can both be marginalized. There's also the model of saying what the typical locations are for a particular object. That can be marginalized as well. And so just to give you a rough idea, in our current implementation on a data set of about 700 images, training took a day or two on a single processor. There's a lot of opportunities for parallelization here. And testing takes 1 to 2 minutes for each result image I'm going to show you. And so here's some example segmentations of test scenes. And so here there's, again, these ellipses here are these features that were detected in a low-level fashion. And I've colored each feature by the object category that is sort of most likely to have generated it. So blue is road, purple is building, red is car, green is tree. I should point out we're not using color, so we're just using grayscale. And that's part of the reason why we're not doing a fantastic job with the tree features. We do a much better job if we did color features. On the right here, this is one of the worst examples in the whole test set. I'm not going to give it credit for knowing that cars park inside of parking garages. And so there's two things going on here. So one is that with our sort of the local edge and corner features we're using, this pattern of a white bar with some dark above it looks a lot like the patterns you get from the side of a car and the windows above it. The second thing is that in this current version of the model, we don't have any sort of contextual information. So the model doesn't know that cars don't float in the sky above other cars. And so that is sort of one of the big directions in which you would expect to get the most benefit out of these scene models. And it's something that we're sort of trying to think about how to build good models for now. So we also did a sort of, as a baseline, we again looked at the sort of bag of features classified based solely on feature appearance, not position. There's some signal here, but if we sort of look at things computationally, the solid curve is this full model I've described. The black dashed line is the local appearance only. So for all categories, you get a fairly substantial boost in performance by accounting for spatial structure. So now I'm going to give a higher level view of several sort of extensions we've done of this work. And so one is to sort of three-dimensional scenes. And the intuition here is that if I look at this image here at the top, it's really hard to tell just from the pixel cues where the desk begins and the bookshelf in the background ends. So in 3D, on the other hand, the sort of segmentation of objects is easy. Okay, so if I know the 3D structure, that makes it easier for me to separate the objects that are in the scene. Conversely, if I know that I'm looking at a desk and a bookshelf, that's going to make it a lot easier for me to estimate this 3D structure. And so we'd like to sort of put these two problems together in an integrated fashion. So to do this, we can extend the same basic ideas to 3 dimensions. So now I have a set of objects that have parts that live in 3D. To generate each scene I see, I move those objects around to different 3D locations. Then I get a set of features that live in 3D. And finally, I observe the perspective projection of those features into the imaging plane. Okay? And so this is going to let us account and recognize objects that are at multiple scales via the way scaling really occurs, which is by the object moving closer or farther from the camera in 3D. Okay. And so to train this model, we use stereo data. The idea is real simple. I have a pair of cameras side by side. And if I look at a point in the scene, if it's close to me and I move from one camera to the other, I get a big change in its projected location. If it's a point on the mountain far away in the distance, it won't change at all. And so this disparity, or horizontal distance in which it changes, is inversely proportional to the depth. And so what stereo algorithms do is they take features in one image, they look along the corresponding what's called epipolar line in the other image, and look for matches. And so these SIFT descriptors are actually one of the better approaches out there for doing this matching process. But they end up being fairly noisy. So here I've shown if I take each feature and do a sort of greedy local match for this depth reconstruction. So here blue is a bookshelf, red is a computer screen, green is a desk. This is an overhead view of their reconstruction. So you can see there's a lot of features here where the bookshelf really is, but there's also a lot of outliers in which I've estimated those features as being much too close or much too far from the camera. So the idea is we're going to try to use our object appearance models to clean up these depth estimates. So given a data set of about 150 of these stereo pairs of office scenes, here's an example of the sort of categories we learn. And so if you look here first as sort of a close-up view, I have a model for computer screens in which there's sort of parts modeling the features that show up at the corners of the screen, as well as another part getting the texture you get in the middle of the screen. Here's the desk. There's these sort of horizontally elongated parts which are showing how features spread out along the surface of the desk. The models for bookshelves are a bit noisier. What's going on here is there were a fairly small number of labeled examples of bookshelves in the training data. And so I think a larger data set would improve that. And here's just one example of a stereo test image. So I give it a stereo pair at test time, and then we're doing this search in 3D to find a set of objects that will explain the observed image features as well as my noisy depth estimates. And so here's an example. We're given this image. It correctly identifies that there are 2 objects. There's a desk under them. In this case, it decides that the clutter on the windowsill here also looks like a second desk. And then there's a bookshelf sitting on the left. And so given sort of stereo pairs at test time, this works reasonably robustly. Doing the same thing with a monocular, a single image at test time, is a harder problem for which richer sort of ways of capturing spatial structure are needed. And finally, I'm just going to give you a few hints at some other more recent work. So one new project I've been working on at Berkeley is focused instead on low-level image analysis. And so we want to build models that let us do things like remove noise, deblur images, in paint to restore sort of damages to photographs. And something that can let you do all of these things is to build a good model for the statistics of natural images. So what do pictures I take like in the world look like? What's the sort of characteristic behavior? And we really like to exploit the availability of large image collections to do better image processing. And so again, there's this sort of hard problem. It's hard to write down what a natural image looks like, but I can get lots and lots of examples of the sort of textures you get in pieces of natural scenes. And we're going to try to learn models of these from data. And so we're now going to use to a sort of different feature representation that's more suited to image analysis. So we're going to use wavelets. And so the idea is you can think of this as a decomposition of the image into multiple orientations and scales. So I convolve the image with a set of derivative filters at multiple orientations and multiple scales. And this is going to give me another set of sort of images. And the idea here is by going to the wavelet representation, I've gone to a sort of different representation in which the statistics are simplified a little bit and are easier to learn about than in the original pixel domain. And then to model the dependencies among these wavelet compositions, I'm going to use what's sometimes called a quad tree model. So I have a multi-scale tree-structured model. Each node in the tree is going to correspond to a set of wavelet coefficients at different orientations at some particular location and scale. So this node, in this case, might correspond to these 4 coefficients. And then its children are going to correspond to coefficients at the next finest scale at nearby locations. And so the model we learn is, in order to describe how these wavelets evolve, is related to a hidden Markov model. And there's sort of two key differences. Rather than evolving over time, it's evolving in a sort of coarse-defined manner over space and scale. And the second is, rather than allowing just a sort of finite hidden state space, we're going to allow our model to have a potentially infinite set of states and learn their detailed structure from training data. So one of the standard ways of validating these models is image denoising. So here we have the input image, it's Barbara, a very famous test image in the image processing literature. And here we have it corrupted by added white Gaussian noise. And so people measure the quality of how your estimate works in the original in terms of what's PSNR. It's essentially a logarithmic squared error metric, so larger numbers are better. So here we have 24.6 dB in the original. And so if we apply our denoising algorithm, it raises the quality from 24.6 to 32.1 dB. It's a fairly large improvement. And so to visualize these results, I'm going to do a close-up of this sort of small patch here on the table. It makes it easier to see things on the projector. So again, here's the noisy input patch. This is the output of a method from the image processing literature from the late 90s. It uses that same tree structure, but as a sort of low-order parametric model. Yeah?
Sorry, the noise is Gaussian?
Added white Gaussian noise, which is a bad model for real noise, but nevertheless standard in image processing. Independent per pixel, which actually makes it correlated in the wavelet domain. Yeah. So here's the output of this model. So it's like the tree model I gave you, but just 2 states per pixel, essentially saying, is there an edge or is there not an edge? It's somewhat improved, but if I use these Dirichlet process methods, this is the output reconstruction I get. And so I'm going to go bounce back and forth in these a couple times. And you'll see you get a sort of dramatically better reconstruction of this striped texture relative to the simple 2-state model, and also much better smoothing of the object sitting on the middle of the table. And so what's going on here is what the model has done is if I go back to the input image, there's actually quite a bit of this striped texture. And so what it's done is it's created not just one state, it's created a whole set of states that describe how wavelet coefficients evolve across position and scale in this striped pattern. And then by aggregating that over all the striped areas, it's able to learn a good model of that and get much better denoising performance than you could with the simple low-order model. And then as a baseline, here's what's a related model, a local Gaussian scale mixture model. And here the idea is I'm going to denoise each coefficient independently given a local neighborhood. And so if I compare this to our results, you'll see that it's reasonable, but there's sort of extra cloudiness in which the stripes aren't reconstructed quite as well. And so this local GSM model was state of the art until a year or two ago. It's still considered one of the better denoising methods. But it's hurt in this case because it can't use the sort of whole image to learn a better model of what this texture looks like. And so what I just described was learning from a single image, and where we're trying to go with this now is saying, well, if I don't have just a single image, I have a whole set of training images. Can I learn a sort of better model which will let me do a better job of processing my corrupted image? One other exciting future direction is in natural image segmentation. And here I have a sort of set of data from the Label Me data set put together by some colleagues of mine at MIT. And so here there's multiple scene categories, coasts, forests, mountains, and so on. Each of them a person has gone through and segmented out regions that are interesting and also given them object categories. And so what we're trying to look at is whether by looking at large sets of images like this way, can we do this thing in an automated fashion? Can we discover what the set of regions are and the patterns by which they're shared across images? And so we've been, I'm not going to have time to talk about it, but we've been able to do some statistical validation to show that a variant of these non-parametric priors is actually a very good fit for the segmentation data. And we've gotten some very promising results here. And so where we really want to go with this is sort of scaling these methods to be able to look at really large data sets, like the ones available on Flickr, where we have huge sort of sets of data that are tagged in a very noisy way. And so the interesting thing is, what can we do to exploit this weakly or partially labeled data to learn more about images? So the non-parametric models I've talked about have a lot of sort of, I think, real advantages to them and let you do interesting things like transfer knowledge among object categories, do learning from small data sets, discover multi-scale appearance patterns that are shared among images. And so the really interesting idea is by sort of combining these sort of flexible forms in this sort of hierarchical way, we can potentially scale non-parametric methods to some really real-world challenging applications. Yeah?
Yeah, when you're finding multiple different kinds of objects in an image, and like you said it takes like 1 to 2 minutes per image, what is it actually doing there? Is it doing something combinatorial to try sets of parts? How
It's running the sampling algorithm, and it's dynamically creating object instances, removing object instances, moving them around, and the sort of there are the things you learn from the training data, which is governed by the data process priors, are sort of governing the way in which you're creating things. And so essentially, you're in some sense, the sampler is doing a sort of local search for sort of stochastic search for configurations of objects that will explain the data, but it's in a sort of a way that's driven by the probabilistic model. And so, you know, as you can run the sampler for longer and longer. The longer you run it, the sort of better your results get. 1 minute's about the point where you get 95% of the performance of running the sampler for a long time.